spatio-temporal feature based on triangulation of this
So as the title suggests, what we propose here is the method of extracting spatio-temporal features. And our method is an extension of the method proposed by Lecure in ECCV workshop 2010. And our contributions are first, a simple yet efficient selection of interest points, and second, some novel spatio-temporal descriptors. And the performance of our feature on UCF 101 was about 60%, and we applied this vector encoding technique to represent the videos within our feature, and we used non-linear SVM to perform maximum classification. And so here I want to compare our work with some works also and to extract low-level spatio-temporal features based on interest points. Here I list only some of them: tree shape, tree hop, stick, and trajectory. Here the trajectory means dense trajectory-based features as described in Wang et al.'s paper. And there are 2 points that I want to compare. First, the selection of interest points, and then the vectorization of the features. And first about the point selection. Why 3D SIF randomly select points? 3D hop and stick use the space-time Poisson Harris operator to select those points. And lens trajectory use lens sampling to sample the points. And on the other hand, our proposed method first use lens sub to sample points, and then we select interest points based on the flow vectors of the key points. So our idea is quite similar to the previously presented work, because we consider the points with more movements, with more dominant movements, are supposed to be more representative. And about the vectorization, 3D SIF, 3D hop, and stick extract the features from the cuboid, the area surrounding of the interest points, and lens trajectory also extract features from the surrounding interest point, but the volume is aligned with the trajectory of the interest points. And our proposed method does not use the information of the surrounding area. Indeed, we group the interest point into triangles, and then we extract features from each triangle. And here I use a frame set of fencing action to illustrate our method. So first, from a frame set, we extract the soft key points using lens sub, and then we estimate the optical flow using large displacement optical flow. And here the key points and their flow vectors indicated by the red dots. And then we operate motion compensation and point selection. You can see that after the point selection step, only the points that belongs to the more representative areas are selected. And then we apply delay triangulation to the selected points, and then finally extract spatio-temporal features from each triangle. And so basically our framework is constructed based on the baseline, but we introduce the motion compensation, and we improve the point selection step and the feature extraction step. So here I will talk about our enhancement points. First about the motion compensation. So in the baseline, no motion compensation is done. That means when they detect the camera motion in a frame set, they ignore the information of that frame. And if the whole camera contains camera motion, that means no features will be extracted. And we propose a simple yet efficient motion compensation to overcome this problem. And we first estimate the direction and the magnitude of the camera flow, and then if we determine that the camera is moving, we cancel the camera motion from the key points. And here's how we estimate the camera movement. We consider four directions: right, left, up, and down. And so here's an example for horizontal direction. We first count the number of the points with positive and negative optical flow, and we then consider the points with have the absolute flow is larger or equal to the constant as a moving point. And then if this condition is satisfied, the camera is considered as being moving to the right. And if this condition is satisfied, the camera is considered to move left. And this condition simply means that if the majority of the points moving to a direction, so the camera is moving to that direction. And if none of these conditions is satisfied, the camera is horizontally stable. And so in this case, it's not necessary to compensate the motion. And if the camera is moving, the magnitude of its movement is simply computed as an average of flow points in the same direction. And in this case, the motion of the key point will be simply compensated like this, minus or plus the camera flow just depends on the direction of the camera. And after determining which point are moving and how many times they move in the frame set, we select the interest points. So let me explain the principles of conservation. In the baseline, through the frame set, for point if at least once its flow is larger than a fixed threshold, that point will be selected. As opposed to the method, in our method, the threshold is flexible. It changes at every frame, and moreover, not all the points which satisfy the first condition will be selected, but we prefer points with more movements. So first, why motion threshold should be flexible? First, because this is the magnitude of the movement depends on the action. So, for example, the sport action like surfing, high jumping, or ice dancing are supposed to have larger displacement than the daily activities like flying lipstick, like typing or surfing. And it also depends on the environment. So, for example, even with the same action, the further the distance between the actors and the camera, the smaller the movements will be. So, and the environment can change at any time. So, we propose to update the motion threshold at every frame, and we consider four directions, right, left, and up and down. And so, for example, the motion threshold for frame in the right direction will be estimated that, and it's just the value, some value between the average and the maximum. And so if a point has the flow larger or equal to the threshold of a direction, then the point is considered to be moving into that direction. And we also consider the case when nothing is moving to a specific direction. So if the threshold of that direction is smaller than epsilon, the point is no point is moving to the direction. And in our experiment, epsilon is fixed as 1. And then after determining which points are moving and how many times they move, we select the points with more movement. So why points with more movement should be preferred? Because they are supposed to be more distributed. So for example, the materials in cutting scene or the referee in the sumo wrestling scene also move to some transit, but they do not move frequently than scene of the sumo in the sumo wrestling scene. So points with more are supposed to be more representative. And so we greedily select the interest points based on the number of their movements. And so the points with more movements will be first. And if when the number of selected points exceeds the predefined number, the selection will stop. And after point selection, we apply the Yanai triangulation to the selected points, and we obtain some triangles, and then we extract from each triangle special descriptors, temporal descriptors, spatio-temporal descriptors, and concatenate them one by one to obtain our proposed feature. And so for special descriptors, following the baseline, we concatenate the sub-descriptors.
In this one, can you go back to the previous thing?
Okay.
So you just select these interest points, but you don't have the correspondence of the points in this frame to that frame. You work on these trajectories, right?
You mean the trajectories?
Yeah.
Yeah.
Do you have that?
Yes, I have the. I use the optical flows, trajectories of the points.
From frame to frame.
Yeah, from frame to frame. Actually, this is trajectory. Let me use the trajectory of the points.
But you just connect these like.
Yes. Yeah. And we concatenate the sub-descriptors of 3 points of the chip to form a 192 dimensional descriptor. But this descriptor is quite long and may contain repeated information. So we apply PCA to reduce the dimension, and we call the dimension reduced descriptor as PCA itself. It is 96 dimensional descriptor. And for temporal descriptors, we extract the histogram of optical flow and histogram of direction of flow. And so basically, these descriptors are based on the optical flow of the interest points. And so we were following the histogram of optical flow. We bin each flow vector to be histogram. The binning is according to the primary angle to the horizontal direction, and it's weighted by according to the magnitude of the flow. And then finally the histogram is normalized to somewhat to 1. And for the histogram of direction of flow, the flow vector is being following the baseline, and based on the direction of the movements, the so-called directions, and it's also normalized to somewhat to 1. And for spatio-temporal descriptors, we extract the 3 following descriptors. An area triangle is formed by combinating the areas of the triangles, and this following the baseline. And we propose 2 novel descriptors that we call as histogram of angle of triangle and histogram of angle of flow. And so, what's the idea to these descriptors? To better explore the set characteristics of the triangle and the motion, the optical flow motion of the interest points, we propose to investigate these angles. And so for histogram angle triangle, the 2 smallest angles of each triangle are being to histogram according to its magnitude, and each triangle is weighted by sum of the magnitude of its 2 edges. And for histogram of angle of flow, the angle set by adjacent trajectories are being similarly to each histogram of origin optical flow, and is weighted by sum of its 2 edges. And So this is a summary of our proposed descriptors. It's a combination of following descriptors. For HOF, AT, and AF, the dimension can change according to the length of the frame set, and except for PC itself, all of them are normalized somewhat to 1 again. And the final descriptor is 180 dimensional vector. And so after feature extraction, we apply vector encoding to encode the videos, and we use multiplex linear SVM to perform simple classification. And we conduct experiments on UCF 101 dataset and compare our method with the baseline and the dense trajectory-based features. And here's the results. And as you can see, our proposed feature significantly improved the baseline, and we achieved a little bit slightly better results than dense trajectory-based feature. And we also combine our feature with dense trajectory-based features, and using early fusion and obtain this result. And this result, 66% is the result that we submitted to the Chinese. So, in conclusion, we propose a method of extracting Spatio-Temporal features, and we improve the baseline and achieve better results than trajectory-based features. And in the future, we would like to handle more complicated parameters. We would like to consider in Z direction. For example, when camera move forward and backward, we want to handle this case, and we want to comply with other features.
So for motion compensation, if you use the homography applying take it out, zoom in.
Yeah.
So it's like kind of pretty good.
And this upload we are going to start from 2:30. And for the action